Welcome, curious minds. Today, we embark on a journey into the fascinating world of quantum mechanics. Today, we dive into quantum mechanics, the branch of physics that deals with the behavior of the smallest particles in the universe, the science of the super small. We're talking about particles so tiny that they defy our everyday understanding of reality. Think atoms and the particles inside them, electrons, protons, neutrons. These are the building blocks of everything around us. These tiny things play by a completely different set of rules. Unlike the predictable world we see every day, the quantum world is full of surprises. Our everyday world is predictable, governed by classical physics. We can predict the motion of a car or the fall of an apple with great accuracy, but at the quantum level, things get weird. Particles can exist in multiple states at once, and their behavior can be influenced just by observing them. Quantum mechanics describes this weirdness, showing us how these particles behave. It's a set of rules that are completely different from what we experience in our daily lives. They can be in multiple places at once or pop in and out of existence. This phenomenon is known as superposition and quantum tunneling. Imagine zooming into a TV screen to see individual pixels. Each pixel is like a quantum particle, following its own set of rules. Quantum mechanics is like understanding the rules for those pixels. It helps us make sense of the smallest components of our universe. It's the instruction manual for the universe at its most basic level. Without it, we wouldn't understand the fundamental principles that govern everything. Why care about these tiny rules? They're not just obscure theories. They have real-world applications that impact our daily lives. Quantum mechanics is the foundation of much of our technology. From MRI machines to solar panels, it plays a crucial role in modern advancements. It explains how the sun shines and how chemistry works. The reactions that power our sun and the processes in our bodies all follow quantum rules. It's the reason computers and smartphones exist. The tiny transistors in these devices operate based on quantum principles. Understanding it unlocks a deeper understanding of reality itself. It challenges our perceptions and opens up new possibilities for innovation. So, buckle up. The universe is about to show you its quantum side. It's a mind-expanding adventure. Are you ready? Let's dive into the quantum realm together and explore the mysteries that lie within. Our quantum journey begins over a century ago, in an era where the foundations of classical physics were being questioned. In the late 1800s, physicists thought they had most things figured out. Newtonian mechanics and Maxwell's equations seemed to explain the physical world comprehensively. But then some pesky problems appeared, like the ultraviolet catastrophe. This was a major issue in the study of blackbody radiation. Classical physics predicted infinite energy radiation at high frequencies, which didn't happen. This discrepancy puzzled scientists deeply. Enter Max Planck, who proposed a groundbreaking idea. Energy comes in tiny packets called quanta. This was a radical departure from the continuous energy concept. Planck's idea solved the ultraviolet catastrophe perfectly, laying the groundwork for quantum theory. His radiation law matched experimental results precisely. Then came Albert Einstein, who tackled another perplexing problem, the photoelectric effect. Classical wave theory couldn't explain why light could eject electrons from a metal surface. He proposed that light behaves like a stream of energy packets or photons. This particle-like behavior of light was revolutionary. This explanation of the photoelectric effect was so compelling that it earned Einstein a Nobel Prize in 1921, cementing the concept of photons in physics. Niels Bohr then applied these quantum ideas to the structure of the atom. He suggested that electrons exist in specific energy levels or orbits around the nucleus. Electrons could jump between these levels by absorbing or emitting quanta of energy, explaining atomic spectra. This model explained why atoms emit light at specific frequencies, a phenomenon that classical physics couldn't account for. The field of quantum mechanics was truly born, revolutionizing our understanding of reality. It opened up new realms of scientific inquiry and technological innovation, forever changing the landscape of physics. Let's dive into the fascinating concept of wave-particle duality, a truly mind-bending idea from the world of quantum physics. This concept challenges our everyday understanding of how things work. At the quantum level, Particles can exhibit properties of both waves and particles simultaneously. This duality is one of the most intriguing aspects of quantum mechanics. Take light, for example. It behaves like a wave, spreading out and creating interference patterns, but it also acts like a particle known as a photon. When light bends around corners or creates interference patterns, it demonstrates classic wave behavior. This phenomenon is beautifully illustrated in the famous double-slit experiment. However, light also behaves like a particle. When photons hit a surface, they transfer energy in discrete packets, showcasing their particle nature. Quantum mechanics tells us that the behavior of light depends on how we measure it. The act of measurement itself influences whether we observe wave-like or particle-like properties. This wave-particle duality isn't limited to light, it applies to matter as well. Electrons, for instance, can exhibit both wave-like and particle-like behavior. Electrons can diffract and create interference patterns, much like waves do. This wave-like behavior of electrons is crucial in understanding the nature of matter. When electrons are passed through a double slit, they create interference patterns, further proving their wave-like nature. This dual nature of wave and particle is a fundamental aspect of everything in the universe, from the tiniest particles to the largest cosmic structures. For larger objects like us, the wavelength is so tiny that we can't detect it. This is why we don't observe wave-particle duality in our everyday lives. But for tiny particles, this duality is a significant and observable phenomenon. It's a concept that truly blows the mind and reshapes our understanding of reality. Enter the uncertainty principle, introduced by Werner Heisenberg. It states you can't know certain pairs of properties of a quantum particle with perfect accuracy at the same time. The more precisely you know one, the less precisely you know the other. The most famous pair is position and momentum. The act of measuring affects the quantum system. Particles don't have definite properties until measured. They exist in a state of probabilities, a haze of possibilities. The uncertainty principle introduces an inherent fuzziness into reality. Quantum mechanics, with its uncertainty, says the universe is more subtle, more surprising than that. Quantum mechanics isn't just for physicists, it's in your pocket. Lasers in Blu-ray players and barcode scanners rely on quantum mechanics. Transistors, the building blocks of electronics, operate on quantum principles. Without quantum mechanics, the digital revolution wouldn't have happened. MRI, solar panels, and drug development all rely on quantum interactions. Next time you use your phone or watch a movie, thank the quantum realm. Quantum mechanics is about understanding the fundamental nature of reality. It governs nuclear fusion, the process powering stars. Quantum mechanics is the language of chemistry, explaining molecular interactions. It forces us to confront big questions about reality and observation. The universe is far stranger and more interconnected than we imagined. Quantum mechanics expands our cosmic perspective and is a continuous journey of discovery. The quantum revolution is still unfolding, promising astonishing breakthroughs. Quantum computing could solve problems impossible for classical computers. Quantum cryptography offers truly unbreakable codes. Quantum mechanics will continue to fuel our quest for understanding the cosmos. The journey into the quantum world is a journey towards understanding our origins and our universe. The quantum future is bright. The cosmos awaits our next great leap.